The Little Blue River cut cold through eastern Nebraska in the winter of 1871 when Johann Schmidt's cabin walls turned to ice inside and his water bucket froze solid just 3 feet from his blazing stove. He had built his homestead exactly like every settler manual said to build it. Raised timber frame, shallow foundation, plank walls chinked with mud, fast and standard. By spring, he had burned through 8 cords of firewood and still woke to frost on his bed sheets. Come summer, the same cabin baked to over 100 degrees by afternoon. Across the Nebraska plains, homesteaders were losing the same battle in cabins built by the book and failing by the season. Neighbors called him crazy when Johann started digging into a hillside instead. But over the next 3 years, he quietly applied an old method that kept his dugout home at 55 degrees year-round with just 2 cords of wood. While raised cabins kept failing through brutal winters and scorching summers, Johann's earth-coupled dwelling stayed comfortable without constant heating or cooling. In this video, I'll break down the exact steps, measurements, and principles behind his forgotten technique that modern builders are rediscovering today. What did Johann understand about working with the Earth's natural temperature that every homesteader building above ground completely missed? Johann Schmidt stepped off the Union Pacific rail car in Grand Island, Nebraska Territory in the spring of 1869 with a carpenter's chest, $43, and the confidence that came from building timber houses in the Hartz Mountains for 15 years. The homestead office clerk handed him a map to a quarter-section claim 8 miles south of the Little Blue River and advised him to get a cabin up fast before the first snow. Every settler guide Johann had read on the journey west said the same thing. Build above ground, use local timber, raise the floor on posts to keep moisture out, and get 4 walls and a roof between you and winter as quickly as possible. The method seemed sensible enough. Cottonwood and elm grew thick along the river bottoms. The railroad had delivered planks and nails to Grand Island, and Johann could see a dozen other homesteads scattered across the rolling prairie, each built the standard way. Thomas Parker, who had been settling claims since 1870 and acted as an unofficial building foreman for new arrivals, walked Johann through the accepted technique. Dig shallow post holes about 2 feet deep, set your corner posts and floor joists. Raise the structure 18 inches off the ground for air circulation. Frame the walls with 2x4 timbers, spaced 16 inches apart. Sheath with inch-thick planks, and chink the gaps with prairie mud mixed with grass. Parker had overseen the construction of 18 such cabins and assured Johann that this was how frontier building got done. Johann followed the plan precisely. He cut his timber that summer, hauled it to his claim, and by late September had raised a 16 by 20-foot cabin with a stone chimney on the east wall and 2 windows facing south. The structure looked solid and matched every other homestead within 10 miles. He chinked the walls carefully, built a raised plank floor over the post foundation, and installed a cast-iron stove he had ordered from a supply catalog. When the first snow fell in November, Johann felt confident he had built himself a proper home. The failure came gradually, then all at once. November brought steady cold that seemed to seep through the plank walls despite the mud chinking. December delivered the killing blow when a 3-day blizzard drove temperatures to 20 below zero, and Johann discovered that his raised floor had become a wind tunnel. Cold air poured up through the gaps between the floorboards. The thin walls radiated cold inward, and the stove struggled to heat the drafty interior. By January, Johann was burning cord after cord of precious firewood just to keep the cabin minimally livable, and still he woke each morning to find his wash water frozen solid. Spring brought no relief, only a different torture. As soon as the sun climbed higher in the sky, the same thin walls that had leaked heat all winter began absorbing and trapping every ray. The raised timber floor, which was supposed to provide healthy air circulation, instead created a pocket of superheated air that rose through the floorboards. By June, afternoon temperatures inside the cabin regularly exceeded 100 degrees, making work impossible and sleep a misery. Johann rigged canvas over the windows and opened both his door and the single window, but the relief was minimal and temporary. Walking to Thomas Parker's cabin in early July to discuss his struggles, Johann discovered he was not alone in his misery. Parker's wife mentioned that they had given up cooking indoors during daylight hours because the cabin became unbearable. Another neighbor, Samuel Baker, had moved his family to sleep outside under a canvas shelter because their raised cabin trapped heat like an oven. The pattern was consistent across the settlement. Every cabin built according to the accepted frontier, wisdom was failing to provide basic comfort, despite consuming enormous quantities of firewood and requiring constant adjustments. It was during one of these conversations that Johann first heard about the Pawnee Earth Lodges. Samuel Baker mentioned seeing the partially underground structures during a supply run to the reservation and dismissing them as primitive. But Johann found himself curious about how indigenous people had solved the problem of prairie climate extremes without access to railroad timber and cast iron stoves. When he mentioned this interest to Parker, the older settler laughed and warned Johann against adopting Indian ways that would mark him as an outsider among serious homesteaders. The mockery intensified when Johann began asking questions about building into hillsides instead of above them. Parker and several other established settlers made it clear that proper Americans built proper houses, not holes in the ground. The local supply agent in Grand Island told Johann that dugouts were temporary expedients for desperate people, not suitable for permanent settlement. Even the homestead office clerk suggested that earth shelters would hurt Johann's chances of proving up his claim because they did not demonstrate the kind of substantial improvement that the Homestead Act required. But Johann kept thinking about the fundamental problem. Every cabin in the settlement was fighting the same losing battle against temperature extremes, burning through enormous amounts of wood and failing to provide basic comfort. The accepted wisdom was clearly inadequate, yet everyone continued following it because it was accepted. In the Hartz Mountains, Johann had seen stone houses built partially into hillsides that stayed cool in summer and required minimal heating in winter. The principle seemed applicable to Nebraska, even if the materials and techniques would need adaptation. By late summer of 1871, Johann had made his decision. He would test a different approach, even if it meant enduring the ridicule of his neighbors. He scouted his claim and identified a south-facing bank where he could dig into the earth while still providing good drainage and access. The idea was still half-formed in his mind, but the central insight was becoming clear. Instead of fighting the prairie climate with thin walls and raised floors, he would couple his dwelling to the earth's natural temperature stability. Whether this would work remained to be proven, but the conventional method had already proven itself a failure. Johann began his excavation on the first cool morning of September 1872, marking out a rectangle 16 feet wide by 20 feet deep against the south-facing bank he had selected. The location offered natural drainage away from the slope, protection from north winds, and enough elevation to prevent water pooling during spring runoff. Using a spade and mattock, he started cutting into the dense prairie sod, working methodically to maintain straight walls and a consistent depth. The work proved more challenging than expected. 3 feet down, Johann encountered a layer of clay that turned sticky and difficult to move when wet, followed by a stratum of sandy soil mixed with small stones. At 4 feet, the earth felt noticeably cooler against his hands, and by the time he reached 6 feet of depth, the soil temperature remained constant even during the hottest part of the day. This observation would prove crucial, though Johann did not yet understand its full significance. His first teacher appeared unexpectedly during the third week of excavation. Red Plume, an elderly Pawnee man who occasionally traded at the settlement, stopped to watch Johann's progress and commented in broken English that the white man was finally learning to build like his people. Through a mixture of gestures and simple words, Red Plume explained how earth lodges used the ground's natural coolness to stay comfortable. He showed Johann how the Pawnee dug their floors slightly deeper than the surrounding earth and always ensured water could drain away from the living space. Red Plume demonstrated a critical technique that Johann had not considered. Using a stick, he showed how the floor should slope gently downward from the back wall toward the entrance, creating a grade that would carry any moisture out of the dwelling rather than allowing it to pool. The slope needed to be subtle, about 1 inch of drop for every 8 feet of length, enough to move water but not so steep as to make the floor uncomfortable for daily use. The drainage lesson became urgent when October rains filled Johann's excavation with 6 inches of standing water. The soggy mess convinced him that Red Plume's advice was essential, not optional. Johann spent 2 days bailing out the water and reshaping his floor to create the proper grade. He cut a shallow channel from the low point of his floor to a drainage outlet 20 feet away from the hillside, ensuring that any future water would have a clear path to escape. The second crucial teacher arrived in the form of Hans Keller, a German immigrant who had homesteaded 12 miles east the previous spring. Keller had worked in the Harz mountain mining region before emigrating and understood drainage techniques that most farmers never learned. When he saw Johann's excavation, Keller immediately recognized the potential for frost problems and water infiltration. He offered to show Johann how German cellars and partially underground buildings managed moisture and foundation stability. Keller's most important contribution was his knowledge of French drainage, a technique used around European cellars to intercept groundwater before it reached the foundation. Together, they dug a trench along the uphill side of Johann's excavation, 6 inches wide and 8 inches deep, running the full length of the dwelling and extending several feet beyond each end. This trench would capture water flowing down the hillside during spring melts and heavy rains, channeling it around the dwelling rather than allowing it to seep into the living space. The German also insisted that Johann install a gravel base beneath his floor planks. They hauled crushed stone from a creek bed 3 miles away, spreading it 3 inches thick across the entire floor area. This gravel layer would provide drainage beneath the floor, prevent direct contact between the wooden planks and damp earth, and create an insulating airspace that would reduce heat loss. The technique required 2 full days of hauling stone with Johann's wagon, but Keller assured him the effort would prevent the floor rot and dampness that plagued many earth-sheltered buildings. With the drainage systems in place, Johann could observe the thermal behavior of his excavated space. During late October nights, when surface temperatures dropped to 30 degrees Fahrenheit, the air 4 feet down in his excavation remained steady at 48 degrees. During November days, when the prairie surface warmed to 55 degrees, the excavated space stayed at the same 48 degrees, demonstrating the Earth's natural temperature buffering effect. The floor installation required careful attention to the drainage grade. Johann laid his planks running parallel to the slope, allowing any moisture that might penetrate the wood to flow along the grain toward the drain outlet. He left small gaps between the floorboards to allow air circulation through the gravel base, but sealed these gaps on the upper surface to prevent drafts. The completed floor felt solid underfoot and showed no tendency to shift or settle despite the unconventional foundation. By December, Johann could measure the effectiveness of his foundation work. Samuel Baker's raised cabin, built using standard techniques, recorded interior temperatures of 30 degrees during a cold snap, while the air in Johann's excavated space never dropped below 50 degrees. The difference of 20 degrees represented the thermal benefit of coupling the dwelling to the Earth's stable temperature zone rather than exposing it to surface weather extremes. The drainage systems proved equally effective. During a January thaw that left standing water around most homestead buildings, Johann's excavation remained dry. The French drain carried runoff away from the hillside. The graded floor channeled any seepage toward the outlet, and the gravel base prevented moisture from reaching the wooden floor planks. Baker's cabin, meanwhile, developed ice dams around the foundation posts and wet spots on the floor where ground moisture had worked its way up through the raised structure. Johann's wood consumption during his first winter in the excavated shelter dropped to 2 cords compared to the 8 cords he had burned in his raised cabin the previous year. The 50-degree base temperature of his foundation meant the stove only needed to add 15 degrees of heat to reach comfortable living temperatures, rather than fighting to warm air that started at outdoor temperatures and leaked continuously through raised floors and thin walls. The success of the foundation established the principle that would guide Johann's complete dwelling system: work with the Earth's natural temperature stability rather than fighting against surface weather extremes. Johann's first attempt at cutting sod blocks in March 1873 produced irregular chunks that crumbled when he tried to stack them. The prairie grass roots had not yet awakened from winter dormancy, and the soil lacked the binding strength needed for construction blocks. Hans Keller, observing Johann's frustration, explained that successful sod cutting required the right season and the right technique. The grass needed to be actively growing to provide maximum root density, and the soil needed enough moisture to hold together, but not so much that the blocks became muddy. By late April, conditions were perfect. Keller demonstrated the proper cutting technique using a sharp spade to slice through the prairie sod in uniform rectangles. Each block measured 24 inches long by 12 inches wide by 4 inches thick, dimensions that provided the optimal balance between handling weight and structural stability. The grass side went down when laying the blocks, allowing the roots to interweave and bind the wall together as the sod dried and settled. The most critical aspect of sod wall construction was the laying pattern. Keller showed Johann how Austrian builders alternated each course, placing blocks lengthwise in one row, then crosswise in the next, creating an interlocking bond that prevented the wall from splitting along vertical lines. This technique, borrowed from stone masonry, gave the earthen wall structural integrity that simple stacking could never achieve. The crosswise blocks acted as ties, binding the wall together across its full thickness. Johann began his walls at the maximum thickness of 36 inches at the base, tapering gradually to 24 inches at the top. This taper served two purposes. It provided a stable foundation for the heavy earthen structure, and it created the maximum thermal mass where heat loss was greatest, at ground level where cold air naturally settled. The thick base also distributed the weight of the roof across a broader foundation, preventing settling and cracking. Red Plume returned during the wall building phase and observed Johann's technique with approval. Through gestures and broken English, the Pawnee elder explained how earth lodge builders use similar principles of mass and thickness. Red Plume showed Johann how to test the quality of each sod block by pressing his thumb into the grass roots. Good blocks resisted the pressure and showed dense, interwoven root structure. Weak blocks crumbled or felt spongy and would not provide reliable structural support. The Pawnee also demonstrated a crucial detail about wall construction that Johann had not considered. Red Plume pointed to the corners where two walls met and showed how the sod blocks should overlap like the fingers of clasped hands, not simply butt against each other. This overlapping technique, called bonding the corners, prevented the walls from separating under the weight of the roof and the pressure of seasonal expansion and contraction. As the walls rose, Johann began to understand the thermal properties of massive earthen construction. During hot May afternoons, when the outside temperature reached 90 degrees Fahrenheit, the exterior surface of his sod walls felt warm to the touch, but the interior surface remained cool. The thick mass of earth absorbed heat slowly and released it gradually, preventing the rapid temperature swings that plagued thin-walled buildings. The most challenging aspect of the construction was the roof system. Johann needed a structure that could support the weight of an earth-covered roof while spanning the 20-foot width of his dwelling. He cut cottonwood poles 8 inches in diameter and laid them across the width of the building, spacing them 18 inches apart from center to center. These main roof beams rested in notches cut into the top course of the sod walls, distributing the weight evenly across the entire wall structure. Over the main beams, Johann laid smaller poles and branches in the opposite direction, creating a grid that would support the roof covering. He then spread a layer of prairie grass and willow brush over this framework, creating a mat that would prevent soil from falling through the gaps between the poles. The brush layer needed to be thick enough to support the earth covering, but not so thick that it would hold moisture and rot. The final roof covering consisted of 6 inches of soil, topped with a layer of prairie sod laid grass side up. This living roof provided both insulation and waterproofing, with the grass roots creating a tough membrane that shed water, while the soil beneath provided thermal mass. The total weight of the earth-covered roof approached 4 tons, requiring the structural support of both the thick sod walls and the carefully spaced pole framework. Johann completed his dwelling in June 1873 and immediately began measuring its thermal performance. During a heat wave that pushed outside temperatures to 105 degrees Fahrenheit, the interior of his sod house never exceeded 58 degrees. The thick walls and earth-covered roof acted as a thermal battery, absorbing heat during the day and releasing it slowly at night, maintaining a stable interior temperature that varied only a few degrees throughout each 24-hour cycle. Samuel Baker visited Johann's completed dwelling during the July heat and marveled at the cool interior temperature. Baker's own cabin had reached 98 degrees that same afternoon, making it uninhabitable during daylight hours. The difference represented more than mere comfort. It meant the difference between a dwelling that could be used throughout the day and one that forced its occupants to seek shelter elsewhere during extreme weather. The structural performance of the sod walls exceeded Johann's expectations. Despite their earthen composition, the walls showed no signs of settling or cracking through the first summer. The interlocking bond pattern distributed stress evenly, while the tapered thickness provided stability without sacrificing thermal performance. The corners, bonded according to Red Plume's technique, remained solid and square. Johann's wood consumption for summer cooling was effectively zero. While his neighbors burned wood to power fans and create cross-ventilation in their overheated cabins, Johann's dwelling required no active cooling system. The thermal mass of the walls and roof provided all the temperature control needed, maintaining comfortable conditions through passive means alone. The contrast with conventional construction could not have been more dramatic. Thin-walled cabins fought losing battles against temperature extremes, while the massive earthen dwelling remained stable and comfortable regardless of outside conditions. By late summer, word of Johann's success had spread throughout the settlement. Several neighbors asked to examine his construction techniques, though most remained skeptical about adopting such unconventional methods. The proof, however, was undeniable. The sod house worked exactly as Johann had hoped, providing superior thermal performance through the simple application of mass, thickness, and earth coupling principles that conventional frontier building had abandoned. Johann's first summer in his completed sod house revealed a problem he had not anticipated. While the thick walls and earth roof prevented overheating, the dwelling's excellent thermal mass also trapped stale air and moisture. By August 1873, the interior felt stuffy and humid, with condensation forming on the cool interior walls during hot afternoons. The same massive construction that solved the temperature problem had created an air quality challenge that conventional thin-walled cabins never faced. The solution came from an unexpected source. Red Plume visited Johann's dwelling during a particularly humid week and immediately recognized the air circulation problem. Through a combination of gestures and simple English, the Pawnee elder explained how traditional earth lodges used a two-level ventilation system to maintain fresh air without losing thermal benefits. High vents near the roof ridge allowed hot, stale air to escape during summer, while low vents near the floor provided controlled fresh air intake during winter when heating was needed. Red Plume demonstrated the principle using smoke from his pipe. He showed how hot air naturally rose to the highest point of any enclosed space, carrying moisture and stale odors with it. A small opening at the ridge level would allow this unwanted air to escape without creating the cross drafts that plagued conventional buildings. The key was sizing the opening correctly, large enough to provide air movement but small enough to prevent heat loss during cold weather. Johann cut his first high vent that September, creating a rectangular opening 6 inches wide by 12 inches long near the peak of his earth-covered roof. He covered the opening with a wooden flap that could be opened during hot weather and closed during winter. The immediate effect was dramatic. Stale air and excess moisture began flowing out of the dwelling, while the thick walls continued to maintain stable temperatures. The low-level ventilation system required more sophisticated engineering. Hans Keller had mentioned that German cellars used earth-tempered air intake tunnels to provide fresh air without the temperature extremes of direct outside air. The principle was simple but effective. Air flowing through an underground passage would approach the temperature of the surrounding soil before entering the dwelling, arriving pre-cooled in summer and pre-warmed in winter. Johann began digging his air intake tunnel in October 1873, starting from a point 30 feet uphill from his dwelling and angling downward to enter through the back wall near floor level. The tunnel measured 12 inches in diameter and 6 feet in total length, sized to provide adequate airflow without excessive heat exchange surface area. He lined the tunnel with flat stones to prevent collapse and installed a simple wooden damper at the interior end to control airflow. The tunnel's entrance required careful positioning to maximize its effectiveness. Johann located it on the northeast side of a small rise, where it would be shaded during summer afternoons and protected from prevailing winter winds. He covered the exterior opening with a grate to prevent animals from entering while allowing free air movement. The tunnel sloped gently downward at a grade that would promote airflow while preventing water accumulation. Testing the system during November revealed the earth tempering effect that made the concept viable. Outside air temperatures varied from 30 degrees Fahrenheit at night to 55 degrees during the day, but air emerging from the tunnel remained consistently near 48 degrees regardless of surface conditions. This preconditioning reduced the energy needed to bring fresh air to comfortable temperatures and eliminated the shock of cold drafts that made conventional ventilation systems uncomfortable. The seasonal control system required one additional element, a method for managing solar heat gain through the south-facing window opening. During summer, direct sunlight streaming through the window could overwhelm even the massive thermal capacity of the sod walls. During winter, that same solar energy represented valuable free heating that should be maximized rather than blocked. Johann's solution was a hinged wooden shutter system that could be adjusted for seasonal conditions. During summer months, the shutters remained closed during the hottest part of the day, preventing unwanted solar gain while still allowing natural light through gaps around the edges. During winter, the shutters opened wide to admit maximum solar radiation, which the massive sod walls absorbed during the day and released gradually during the night. The complete ventilation system created a seasonal operating cycle that matched the dwelling's thermal needs. During summer, the high vent opened to allow hot air escape, while the earth-tempered intake tunnel provided cool, fresh air near floor level. The south window remained shuttered during peak heat hours. This configuration maintained interior temperatures near 57 degrees Fahrenheit, even when outside temperatures exceeded 100 degrees. Winter operation reversed the airflow pattern. The high vent closed to prevent heat loss, while the low intake tunnel continued providing fresh air. The south window opened wide to maximize solar gain during the short winter days. Johann's small stove supplemented the solar heating and earth tempering, but the ventilation system ensured that heated air remained fresh and comfortable, rather than stale and overheated. The humidity control benefits became apparent during Johann's second winter in the dwelling. Samuel Baker's conventional cabin suffered from excessive indoor humidity that condensed on cold windows and walls, creating ice buildup and potential mold problems. Johann's ventilation system maintained indoor humidity at comfortable levels by providing continuous air exchange without the temperature penalties that made ventilation impractical in thin-walled buildings. Air quality measurements confirmed the system's effectiveness. Johann could detect no stale odors or stuffiness in his dwelling, even during extended periods of cold weather when the structure remained sealed except for the controlled ventilation system. Baker's cabin, by contrast, developed the characteristic stuffy smell of inadequate air circulation, despite having more window and door openings than Johann's earth-sheltered dwelling. The wood consumption benefits of the controlled ventilation system exceeded Johann's expectations. During winter 1874, he burned only 1 3/4 cords of wood to maintain comfortable temperatures and air quality. The earth-tempered intake air required less energy to warm to room temperature, while the controlled exhaust prevented the overventilation that wasted heated air in conventional buildings. By spring 1875, Johann had refined his seasonal operating procedures into a simple routine. Summer meant opening the high vent and closing the south shutters during midday heat. Winter meant closing the high vent and opening the shutters for maximum solar gain. The earth-tempered intake tunnel operated continuously, providing fresh air regardless of season, while the thick earthen walls maintained stable temperatures throughout the year. The integrated system of foundation, thermal mass, and controlled ventilation had solved every climate control challenge that defeated conventional frontier construction. The blizzard of January 1882 arrived without warning, dropping temperatures to 28 degrees below 0 Fahrenheit and piling 3 feet of snow across the Nebraska plains in less than 48 hours. The storm caught homesteaders unprepared for its ferocity, trapping families in their dwellings with whatever fuel and food they had stored. For Johann Schmidt, now in his 9th year of earth-sheltered living, the blizzard would provide the ultimate test of his building system against the harshest conditions the prairie could deliver. Thomas Parker's conventional cabin, built in 1876 using the same raised timber frame methods Johann had originally followed, began failing within hours of the storm's arrival. The thin plank walls offered no resistance to the driving wind that found every gap in the mud chinking, while the raised floor became a conduit for frigid air that poured up through the floorboards. Parker's family retreated to a single room around their cast iron stove, burning furniture and fence posts when their prepared firewood ran out after 3 days. Samuel Baker documented the crisis in his journal, recording interior temperatures in his own cabin that dropped to 18 degrees Fahrenheit despite continuous firing of his heating stove. The roof began sagging under the snow load on the 4th day, forcing Baker to prop up the ridgepole with boards torn from interior walls. Ice formed on the inside surfaces of his windows and walls, creating a glazed coating that made the interior feel like a cave carved from frozen ground. Johann's earth-sheltered dwelling responded to the extreme conditions in ways that surprised even him. The massive sod walls absorbed the wind's impact without flexing or allowing air infiltration, while the earth-covered roof distributed the snow load across the entire wall system rather than concentrating stress on individual structural members. Most remarkably, the interior temperature never dropped below 53 degrees Fahrenheit, even when Johann allowed his fire to burn out completely during the storm's peak. The structural advantages of earth-integrated construction became evident as the blizzard continued. Conventional cabins throughout the settlement suffered roof damage as snow accumulated beyond the load capacity of their timber frame systems. Johann's dwelling, with its thick earthen roof already designed to carry the weight of soil and sod, absorbed the additional snow load without stress. The tapered sod walls distributed the increased roof weight across a broad foundation, preventing the settling and cracking that affected buildings with concentrated load points. Air quality remained excellent throughout the extended confinement period. While families in conventional cabins suffered from smoke backflow and carbon monoxide buildup as they overloaded their heating systems, Johann's controlled ventilation system continued operating even in extreme conditions. The earth-tempered intake tunnel delivered fresh air at 46 degrees Fahrenheit, requiring minimal energy to warm to comfortable levels while preventing the dangerous accumulation of combustion gases. Johann began systematic measurements on the 5th day of the storm, using a thermometer borrowed from the settlement's postmaster to document the performance differences between building systems. His records showed that his dwelling maintained a temperature range between 53 and 68 degrees Fahrenheit with only occasional use of his small heating stove. Baker's cabin, measured during the same period, fluctuated between 15 and 55 degrees despite continuous burning of whatever fuel could be found. The fuel consumption calculations revealed the most dramatic difference between the two approaches. Johann burned 1/2 cord of carefully hoarded firewood during the 10-day storm period, using his stove only during the coldest nights to raise the interior temperature from its stable base of 53 degrees to a comfortable 68 degrees. Baker's family consumed everything combustible in their cabin, including furniture, books, and interior wallboards, equivalent to approximately 4 cords of firewood, yet still experienced dangerous cold during the storm's worst moments. When the blizzard finally ended, the contrast between building performance became visible throughout the settlement. Johann's dwelling emerged structurally intact with no damage to repair. The earth-covered roof had shed excess snow naturally as temperatures rose, while the sod walls showed no signs of frost damage or structural stress. His neighbors faced extensive reconstruction work, replacing damaged roof timbers, rechinking walls that had cracked from thermal stress, and rebuilding sections of raised floors that had shifted during the freeze-thaw cycles. The economic impact of the storm created converts to Johann's methods. Baker calculated his storm-related repair costs at $32, representing nearly 3 months of cash income from his wheat crop. Johann's repair bill was $0 and 0 hours of labor. The dramatic difference prompted Baker to ask Johann for detailed instruction in earth-sheltered construction techniques, marking the first formal request for knowledge transfer that Johann had received from his skeptical neighbors. Word of Johann's storm performance spread beyond the immediate settlement through letters and newspaper accounts. The Grand Island Independent published a brief item about the German homesteader whose underground house weathered the Great Blizzard without damage or excessive fuel use, attracting attention from homesteaders throughout the Platte River Valley who were rebuilding storm-damaged structures. Mary Ellis, secretary of the Nebraska Homestead Building Association, visited Johann's dwelling in March 1883 to document his construction techniques for publication in the association's quarterly bulletin. Ellis had initially dismissed earth-sheltered building as unsuitable for permanent settlement, but the storm's demonstration of structural superiority forced a reconsideration of official building recommendations. Her detailed interview with Johann produced the first technical description of earth-coupled construction to appear in territorial settlement literature. The association's bulletin, published in spring 1885, included Johann's techniques under the heading Semi-Subterranean Construction for Prairie Conditions. The publication provided construction details, material specifications, and performance data that allowed other homesteaders to replicate the earth-sheltered approach. Ellis noted in her introduction that conventional above-ground construction had proven inadequate for extreme prairie conditions, while earth-integrated building offered superior thermal performance and structural durability. Within 5 years of the bulletin's publication, over 40 homesteads in the Nebraska Territory incorporated earth-sheltering techniques into their construction. Most followed Johann's basic pattern of hillside excavation, thick sod walls, and earth-covered roofs, though individual builders adapted the system to local soil conditions and available materials. The success rate of these earth-integrated dwellings exceeded 90%, with most providing decades of comfortable, low-maintenance service to their occupants. Johann's techniques influenced building practices well beyond the immediate frontier period. Agricultural colleges in Kansas and Nebraska began teaching earth-sheltered construction in their extension programs during the 1890s, recognizing the fuel savings and structural advantages for rural applications. The principles of thermal mass, earth coupling, and controlled ventilation became standard elements in practical building education throughout the Great Plains region. By 1890, Johann's original dugout had become a demonstration site visited by builders and agricultural agents from across the territory. The structure remained comfortable and structurally sound after 17 years of continuous occupation, proving the long-term viability of earth-integrated construction methods that conventional wisdom had dismissed as temporary expedients.